Deep in the cosmic web, scientists have found something that shouldn't exist, a region of space where the familiar laws of physics seem to simply stop working. Light bends in impossible ways, energy behaves unpredictably, and gravity appears to lose its grip. It's as if the cosmos forgot its own rules, an uncharted realm where physics itself comes undone. A region of space so strange, it shouldn't exist at all. The impossible zone. There are regions in the universe where the rules of reality seem to fall apart, places where physics stops behaving like physics. Astronomers call them singularities, but that word does little justice to their strangeness. They exist at the edges of black holes and at the dawn of time itself, boundaries where space and time stop being separate things and begin to fold into each other. At the surface of a black hole, the event horizon, gravity grows so strong that even light cannot escape. According to Einstein's general relativity, time there slows until it almost stops. Beyond that boundary, the equations collapse into infinities: infinite density, infinite curvature. For scientists, infinity is not a number, it is a warning that the model no longer works. Inside, the mathematics disintegrates, leaving only mystery. Yet nature still functions. Something happens there. We simply cannot describe it. The same breakdown greets us when we look backward to the beginning of everything. The Big Bang, 13.8 billion years ago, was itself a singularity, a point of unimaginable compression, where all energy, matter, and the laws that would later govern them were bound together. Physics as we know it had not yet come into existence. Only as the universe expanded and cooled did gravity, electromagnetism, and the nuclear forces emerge. Before that, there was no rulebook, only an ocean of quantum uncertainty where probability took the place of law. For decades, cosmologists have tried to trace those earliest moments. The cosmic microwave background shows the universe as it was 380,000 years after its birth, when physics already worked predictably. But go further back beyond the first second, or the first trillionth, and the equations again fail. Alan Guth's inflation theory suggests the universe ballooned faster than light, ironing out irregularities. Yet even that elegant idea cannot explain what ignited the process. Whatever existed before that expansion lies deep inside an impossible zone of its own. This collapse of certainty exposes the central tension in modern science. General relativity explains the grand architecture of space-time, while quantum mechanics governs the subatomic world. Each is exquisitely accurate within its domain, but they refuse to reconcile. When both are required at the heart of black holes, or the instant of creation, they tear each other apart. Physicists have spent decades searching for a bridge, a unified theory that could tame these extremes. String theory imagines that everything, from particles to planets, is made of vibrating filaments of energy too small to see. Loop quantum gravity reimagines space itself as a woven fabric of finite loops. Another idea, the holographic principle, proposes that all the information inside a region of space might be stored on its surface, as though the universe were projecting itself from its own edges. If true, even a black hole's hidden core could be governed by rules, just not the ones we currently recognize. The impossible zone is not empty chaos, it is structured beyond our comprehension. Inside it, space may arise from quantum entanglement, and time may emerge from the balance of thermodynamic flow. Cause and effect, the backbone of reality, might be consequences rather than foundations. The universe does not break its laws here, it simply reveals that our version of them is incomplete. For now, these places remain out of reach, their secrets locked behind horizons and hidden in the first instant of existence. Yet their presence shapes everything. Every star, every galaxy, and every atom owes its being to the same laws that crumble at those edges. In confronting these boundaries, we face the humbling truth that understanding has limits. Beyond them, something continues to operate utterly consistent, perfectly real, and still beyond the grasp of human language. Beyond this threshold, light itself begins to distort, bending and vanishing in ways that challenge every certainty we hold about how the universe should behave, where laws collapse. At the farthest limits of understanding, there are regions where the laws that govern the universe lose their certainty. Here, space twists, time stretches, and every rule written into the fabric of physics begins to dissolve. Scientists call these singularities points where the equations of general relativity, normally elegant and precise, break into infinities. They represent places where our models of the cosmos stop working, not because reality itself ceases to exist, but because our mathematics can no longer keep up with it. The best-known singularities sit inside black holes. These objects form when massive stars collapse under their own gravity, compressing matter into a region so dense that space-time curves endlessly inward. At the center lies the point of breakdown, where density becomes infinite and volume shrinks to zero. Einstein's equations predict this collapse perfectly, yet they also declare that no further prediction can be made beyond it. Inside that horizon, causality, the sequence of events that allows one thing to follow another, simply vanishes. It's not that time slows, it ceases to have meaning. The problem is that relativity isn't wrong, it's incomplete. The theory describes gravity as the curvature of space-time, but at the atomic scale, where quantum effects dominate, its smooth geometry becomes meaningless. Quantum mechanics, by contrast, explains the behavior of particles with uncanny precision, yet it cannot describe the geometry of space-time itself. When gravity compresses matter into extreme densities, these two frameworks collide. The result is chaos, the realm where both theories fail to agree, and the very concept of law dissolves. For decades, physicists have tried to bridge that divide. A unified framework, often called quantum gravity, would describe how space-time behaves when both quantum effects and extreme curvature coexist. String theory offers one possible solution, proposing that particles are not points but tiny vibrating strings of energy. Within this framework, singularities may not truly exist. The apparent collapse could be an illusion created by the limits of classical physics. Another approach, loop quantum gravity, envisions space-time as a network of discrete loops, where space itself is quantized. If this is correct, singularities could be avoided entirely, replaced by a kind of bounce in which the collapse of a black hole leads not to a tear in the universe, but to a bridge, perhaps even to another region of space-time. These ideas, while still theoretical, hint that the cosmos may never truly break its own rules. Instead, what collapses is our description of those rules. Even the Big Bang, the beginning of time as we understand it, was once thought to be a singularity. Yet newer models suggest it may not have been a point of infinite density at all, but the result of a transition from a previous cosmic phase. The so-called quantum bounce model, developed through loop quantum cosmology, describes the Big Bang not as a beginning, but as a rebound from an earlier universe that collapsed under its own gravity. If that's true, then the collapse of laws is only apparent. What we see as a limit may be the universe passing from one set of conditions to another, an unseen continuity that our mathematics has yet to reveal. Even Stephen Hawking's work on black hole evaporation proposed that information once thought to be lost forever might be preserved in subtle quantum fluctuations along the event horizon. In his final years, Hawking helped shape the holographic principle, an idea suggesting that all the information within a volume of space is encoded on its boundary. It's as if the universe itself prevents true loss, hiding its secrets on the skin of space-time rather than allowing them to vanish completely. Still, from our perspective, these regions remain the most forbidding in existence. They are not simply dark or distant, they are conceptually unreachable. When we describe them as places, we apply language built for planets and stars, not for zones where geometry and time disintegrate. Yet they remind us of something profound, that the universe is not built upon our understanding of it. The collapse of law is not a flaw in nature, but a measure of our own limits. These boundaries, light itself begins to act as though it no longer recognizes the rules that once guided it, curving, scattering, and vanishing into paths no human equation can yet define, the edge of knowing. There exists a boundary, subtle yet absolute, where the reach of human understanding comes to an end. Astronomers call it the cosmic horizon, the farthest distance from which light has had time to reach us since the universe began. Beyond that invisible wall, 46 billion light-years away in every direction, lies a realm forever sealed from our observation. The universe may continue endlessly beyond it, but its light has not yet arrived, and may never do so. In that sense, the cosmic horizon marks the true edge of knowing, a frontier not defined by matter, but by time itself. This boundary arises from the finite speed of light and the ongoing expansion of space. When the universe was born, some 13.8 billion years ago, light began its long journey through the vastness of the cosmos. Yet as it travels, the fabric of space itself stretches, carrying distant galaxies away faster than the light can cross the intervening distance. Beyond a certain point, they recede at such a speed that their light will never reach us. What lies there continues to exist, but it is cut off from our universe of knowledge. It is not that our instruments are inadequate. No telescope, no matter how powerful, could pierce that veil. The limitation is fundamental, woven into the geometry of space-time. This horizon is not static. As space expands, more galaxies drift beyond visibility each year, their light redshifted until it fades into infrared whispers and then into silence. The James Webb Space Telescope, launched in 2021, captures some of the earliest light in existence. Faint ancient photons emitted by stars just a few 100 million years after the Big Bang. Yet even it is gazing backward through a narrowing window, approaching the opaque fog of the cosmic microwave background. Beyond that, the universe was still too dense for light to travel freely. In every direction, we look as far as physics allows, and beyond that, only mathematics can speculate. Physicists and cosmologists attempt to model what lies outside our horizon, using the laws we can observe inside it. If the universe is truly homogeneous and isotropic, meaning it looks the same in all directions, then what lies beyond is likely similar to what we see. But likely is not certainty. There may be vast regions where physics itself takes on new forms, where different constants govern the behavior of light, gravity, or matter. Some cosmological models, born from inflation theory, suggest that our observable universe is merely one bubble among countless others, each with its own version of physical reality. In those distant bubbles, electrons might not exist, atoms might never form, or gravity might be far stronger than here. These are not mere fancies, they arise naturally from the equations that describe cosmic inflation. And yet, despite our inability to reach beyond this edge, the horizon itself continues to teach us. Through the faint glow of the cosmic microwave background, first detected in 1965 by Penzias and Wilson, we can read the conditions of the early universe with extraordinary precision. Tiny fluctuations in that ancient radiation reveal the seeds from which galaxies would one day grow. They are echoes from a time before stars, before atoms, when the universe was a sea of charged particles and light bouncing endlessly between them. It is a remarkable irony. The farther we look into space, the deeper we peer into the past, approaching a time when time itself was barely underway. The edge of knowing, then, is not a wall but a horizon of curiosity. It reminds us that the universe is not something we stand outside of, but something we inhabit, bound by its history and its laws. What lies beyond may never be known directly, yet its existence shapes everything within. The expansion that hides it from view is the same expansion that carried galaxies into being, stars into light, and eventually, us into awareness. The light from those distant regions continues to fade. We are left with the knowledge that even our understanding is part of the same cosmic process, finite, expanding, and always reaching outward. From this horizon of comprehension, the next mystery unfolds, where light itself begins to twist and shift, revealing the strange and beautiful behavior of energy as it stretches toward infinity. Light that misbehaves. Light, that most familiar messenger of the cosmos, does not always behave as we expect. Under ordinary conditions, it is obedient, travelling in straight lines, reflecting off mirrors, bending gently through glass. Yet in the deeper realms of the universe, light becomes something far stranger. It warps around invisible masses, slows without touching matter, and in the presence of immense gravity can even be trapped completely. To understand the universe, we rely on light, but in the most extreme regions of space, light itself begins to lie. According to Einstein's general theory of relativity, light always follows the curvature of space-time. When gravity bends that fabric, the paths of photons bend with it. Around massive galaxies, this distortion becomes visible as gravitational lensing, a phenomenon first confirmed in 1919 when Arthur Eddington's expedition to the island of Principe photographed the deflection of starlight during a solar eclipse. The stars appeared displaced, as though the sun had quietly rearranged the sky. This was not an illusion. It was space itself bending under the sun's mass. Gravitational lensing is now one of the universe's most revealing tricks. The Hubble Space Telescope has captured arcs and rings of distorted light surrounding galaxy clusters, Einstein rings, where light from distant galaxies has been stretched and magnified by intervening gravity. In these distortions, astronomers can map the invisible scaffolding of dark matter, the unseen substance that makes up most of the universe's mass. In this way, the misbehavior of light becomes a tool, showing us what cannot otherwise be seen. But in the presence of even greater gravity, light begins to falter entirely. Near a black hole, space-time curves so severely that photons spiral around it in circular orbits, known as the photon sphere. Beyond that, they fall inward, unable to escape. What we call the surface of a black hole, the event horizon, is not a surface at all, but a threshold where the escape velocity exceeds the speed of light. Here, light is trapped in an eternal moment, stretched infinitely in wavelength until it fades into darkness. When we look at the shadow of a black hole, as captured by the Event Horizon Telescope in 2019, we are seeing this very phenomenon, light caught in a gravitational whirlpool, orbiting just before it disappears forever. Yet, light's peculiarities are not confined to gravity alone. Quantum mechanics adds a second layer of mischief. In the quantum world, light behaves both as a wave and a particle, depending on how it is observed. The famous double-slit experiment, first performed in 1801 by Thomas Young and later refined with single photons, revealed this duality. When unobserved, light forms an interference pattern like a wave. When measured, it behaves like a particle. Observation itself changes its nature, a result that still unsettles physicists today. In the vacuum of space, light should move at a constant speed, 299,792 kilometers per second. Yet under extreme conditions, even this constant begins to waver. Inside dense plasma clouds near neutron stars, photons interact with magnetic fields so intense they can alter the polarization of light. This effect, known as vacuum birefringence, was confirmed observationally in 2016, verifying a prediction made by quantum electrodynamics decades earlier. Light, under such conditions, doesn't merely travel, it changes its very character, splitting into polarized paths that reveal the ferocity of the forces around it. And then there is Hawking radiation, where the quantum vacuum near a black hole allows light to emerge from darkness itself. Virtual particles born at the edge of the event horizon can separate, with one falling inward and the other escaping as radiation. Over billions of years, this slow leak causes black holes to evaporate entirely. Even in a realm where light should vanish, the laws of quantum mechanics conspire to let it whisper its way back into existence. Light is the oldest storyteller in the universe. Every photon carries a record of where it has been, how far it has travelled, and what it has touched. Yet it is also the universe's most capricious witness, bending, stretching, even vanishing, under conditions that defy intuition. It is through light's misbehavior that we glimpse the true strangeness of reality. As light bends and twists through the deep cosmos, the equations we once trusted to describe it begin to warp as well, leading us to a new mystery where mathematics itself starts to unravel. The vanishing equation. There are places in physics where even mathematics begins to lose its voice. The laws that govern motion, gravity, and energy, so dependable in ordinary space, reach points where their logic collapses. These are the domains of singularity, where equations cease to return meaningful answers, producing infinities instead of solutions. The vanishing equation is not merely a failure of numbers, it is the universe reminding us that our tools of comprehension are temporary. At the heart of every black hole lies this crisis. When a massive star exhausts its fuel and collapses under its own gravity, its core compresses beyond any known limit. General relativity predicts that space-time will curve infinitely inward, a singularity of zero volume and infinite density. But infinity is not a physical quantity. It's a signal that our equations have reached their boundary. Something real exists there, but our mathematics can no longer describe it. Physicists have long searched for a way to reconcile this failure. General relativity, which describes the large-scale structure of space-time, works beautifully until quantum effects become unavoidable. Meanwhile, quantum mechanics, which governs the microscopic world, cannot handle the enormous gravitational energies near a singularity. When we attempt to combine them, both theories break apart. The result is an unresolved paradox, an equation that simply vanishes under its own contradictions. Efforts to repair this divide have produced some of the boldest theories in modern physics. String theory replaces particles with vibrating one-dimensional strings, smoothing out the infinities that plague relativity. Loop quantum gravity takes a different approach, suggesting that space-time itself is discrete, a lattice of finite loops that prevents true collapse. In both visions, the singularity may be an illusion, an artifact of trying to divide the indivisible. In cosmology, the same puzzle appears at the beginning of time. The Big Bang is often described as the ultimate singularity, a point where density and temperature were infinite. But newer models, grounded in quantum gravity, proposed that the universe never began from nothing. Instead, it may have emerged from a prior contraction, a bounce, that replaced the singularity with transition. The equations that once vanished may not have failed, but transformed into something new. The pursuit of a unified theory continues to drive physics forward. In 1974, Stephen Hawking proposed that black holes radiate energy through quantum effects, a result that married relativity and quantum theory in a single, elegant calculation. Yet even his equation, the now famous Hawking formula, contains mysteries that remain unresolved. It suggests that information is never truly lost, only transformed. But how that transformation occurs is still hidden from understanding. To approach these frontiers is to watch mathematics behave like light near a horizon, stretching, distorting, fading. Every major step in physics, from Newton's laws to Einstein's field equations, has expanded the region where reason can operate. Yet the universe always holds something back. The vanishing equation is not an error, it is the next invitation. And as the formulas dissolve at the edge of understanding, new patterns begin to stir subtle harmonies between energy, matter, and space-time that may one day restore what the old equations lost, revealing a deeper order beneath the apparent chaos. When time melts, there are regions in the universe where time, as we understand it, ceases to behave like a steady flow. Instead, it bends, stretches, and at its most extreme, it melts into something unrecognizable. According to Einstein's general theory of relativity, time is not a separate entity, but a dimension woven into the same fabric as space, a continuum that can be warped by gravity and motion. Where that fabric curves most violently, near the immense gravitational pull of black holes or the crushing densities of neutron stars, time no longer moves at a constant pace. It slows, distorts, and finally collapses under the weight of the cosmos itself. This phenomenon, called time dilation, is not theoretical fancy, it is measured fact. When an object approaches the speed of light or enters a region of intense gravity, time for that object slows relative to an outside observer. This was first demonstrated through precise atomic clock experiments. In 1971, the Hafele-Keating experiment flew atomic clocks on commercial airliners around the world. Upon return, the airborne clocks showed measurable differences from those on the ground, confirming relativity's predictions. On Earth, the effect is minute fractions of a second over long journeys, but on cosmic scales, it becomes extraordinary. Near the event horizon of a black hole, where gravity's pull is so immense that not even light can escape, the passage of time stretches to infinity. To a distant observer, a falling astronaut would appear to slow endlessly, frozen on the brink of disappearance. Yet for the astronaut themselves, time would continue normally as they plunged inward. Two realities unfold simultaneously, each true in its own frame of reference. It is a reminder that time is not universal, it is elastic, and its rhythm depends entirely on where you stand in the universe's gravitational hierarchy. The melting of time becomes even more striking when seen across cosmic scales. The universe's expansion is accelerating, driven by dark energy. As galaxies recede faster and faster from one another, the flow of time differs across distant parts of the cosmos. In the far future, regions of space will drift so far apart that their light will never reach each other again. For those distant galaxies, time will seem to stop relative to us. The universe is not ticking uniformly, it stretches and slows in a grand, uneven dance dictated by gravity and expansion alike. Einstein once described the union of space and time as a fabric, but physicists now suspect that this fabric might be granular, perhaps even quantum in nature. Theoretical models in quantum gravity suggest that time itself may not be continuous, but composed of tiny, indivisible moments, Planck times, each lasting just 10^-43 seconds. Below this threshold, the concept of before and after ceases to exist. Time may not be a flowing river, but a series of discrete instants, stitched together by the laws of physics into what we perceive as continuity. Even in the realm of the everyday, we experience echoes of this strange malleability. Global positioning system satellites orbiting Earth must constantly correct for both gravitational and velocity-induced time dilation. Without Einstein's equations, your phone's navigation would drift several kilometers each day. The technology that guides us across cities depends on the same physics that governs collapsing stars. Time melting, then, is not poetic invention. It is the universe's most natural behavior under stress. It bends where gravity is strong, slows where motion is extreme, and breaks entirely at the edge of singularity. At that boundary, where space collapses inward and clocks cease to tick, the distinction between past and future dissolves. Time is no longer something that passes, it is something that happens all at once, frozen and infinite. This strange elasticity of time unfolds across the universe. It reveals the deeper force responsible for its distortions, the hidden architect behind the curvature of space-time itself. Gravity. Gravity's secret game. Gravity is the oldest force we know and the least understood. It binds galaxies, shapes planets, and orchestrates the motion of stars. Yet its true nature remains elusive. Unlike the other fundamental forces, electromagnetism, and the strong and weak nuclear interactions, gravity has never been successfully unified with quantum mechanics. It operates on vast scales, curving the geometry of space and time, but refuses to yield its secrets at the smallest levels. The universe, it seems, plays a secret game through gravity, one we can describe perfectly but not yet explain. Einstein's general relativity replaced Newton's simple vision of gravity as an invisible pull between masses. Instead, gravity became geometry. Matter tells space-time how to curve, and space-time tells matter how to move. This elegant exchange explains everything from the orbit of Mercury to the bending of starlight around distant galaxies. But deeper still, it introduces a cosmic paradox. While gravity shapes everything, it is also the weakest of all the forces. A single magnet can lift a paperclip against the gravitational pull of an entire planet. This weakness hints at something profound. Gravity might not be a fundamental force at all, but an emergent one, a side effect of other interactions occurring at the quantum level. Some modern theories suggest that gravity arises from the collective behavior of microscopic degrees of freedom, much like temperature arises from the motion of atoms. The physicist Erik Verlinde proposed that gravity may even be an entropic force, emerging naturally from the tendency of systems to maximize disorder. In this view, space-time curvature could be a thermodynamic effect, a statistical outcome, rather than a primary cause. Yet gravity continues to surprise us. It drives the expansion of the universe through dark energy, a phenomenon first observed in 1998 when distant supernovae appeared dimmer than expected. If dark energy remains constant, the expansion will accelerate forever, pushing galaxies so far apart that gravity's influence will fade into cosmic solitude. On smaller scales, gravity sculpts the intricate filaments of the cosmic web, drawing matter into vast clusters and voids that define the architecture of the universe. Einstein's equations have passed every observational test, from the precession of Mercury's orbit to the detection of gravitational waves in 2015. Those ripples, tiny distortions in space-time caused by colliding black holes, confirmed one of relativity's last great predictions. They showed that gravity is not a mere force acting through space, but a dynamic motion of space-time itself. The universe, we now know, can quite literally ring. Still, gravity's game remains unfinished. When we look inside black holes, the same equations that predict their existence crumble at their centers. The singularity where curvature becomes infinite marks the place where general relativity must give way to quantum gravity, a theory not yet written. Physicists hope that unifying gravity with quantum mechanics will uncover the rules of this hidden game, perhaps revealing that space and time themselves are emergent phenomena born from an even deeper layer of reality. Until then, gravity continues to perform its quiet work. It anchors galaxies while shaping the passage of time, balancing creation and collapse with exquisite precision. It is both sculptor and stage, the unseen rhythm beneath every motion in the cosmos. And as we follow the contours of this invisible game, another mystery begins to shimmer on the horizon, the strange fabric that may hold all these forces together, stretching and vibrating in dimensions beyond our sight, the tear in space-time. Some regions of the cosmos push the fabric of reality beyond endurance, places where space-time, usually smooth and continuous, ruptures under the weight of gravity. This is not metaphor but mathematics. Einstein's equations predict that when mass becomes infinitely compressed, space-time curves without limit, forming what physicists call a singularity. At that point, all familiar order dissolves. The coordinates of space, the flow of time, even the meaning of before and after lose coherence. The universe's geometry itself breaks apart. Such tears occur most famously at the cores of black holes. When a massive star exhausts its nuclear fuel, the outward pressure of fusion fails, and gravity takes over. The star collapses inward, forcing matter into an ever-shrinking sphere. The more it compresses, the more it curves space-time around it, until the surface becomes an event horizon, a boundary from which light cannot escape. Inside, the collapse continues until, by current theory, density reaches infinity. The singularity marks the point where our physical descriptions end, not because nature stops, but because our equations do. General relativity handles this moment with unsettling honesty. The theory does not break it, merely tells us that beyond a certain threshold, space-time ceases to make sense. The paths of light and matter terminate abruptly, an effect called geodesic incompleteness. It's as though the map of reality runs out of paper and the terrain simply disappears. Yet the tear is not a physical wound, it is a hole in our understanding, a place where the universe continues, but the mathematics cannot follow. Quantum physics, however, resists such infinities. It suggests that the smallest units of space and time are quantized, existing in discrete steps rather than as a continuous field. At scales near the Planck length, about 1.6 times 10 negative 35 meters, the smooth fabric of space-time may be woven from finite loops, preventing true collapse. In loop quantum gravity, for example, the singularity is replaced by a bounce, a point where matter reaches extreme density before rebounding into expansion. What we call a tear could instead be a transition, the death of one configuration of space-time and the birth of another. Other theories imagine even more exotic scenarios. Cosmic strings thin, ultra-dense filaments formed during the early universe may represent permanent wrinkles in space-time, remnants of symmetry breaking in the universe's first microseconds. These structures, if they exist, would bend light around them in precise, predictable patterns. like the distorted reflection of a thread beneath glass. While no evidence of them has yet been found, their existence would confirm that space-time can, under certain conditions, fracture and hold the scars of its creation. And then there are wormholes, solutions to Einstein's field equations that link separate regions of space and time through narrow tunnels of warped geometry. A wormhole can be thought of as a tear that reattaches elsewhere, sewing together distant corners of the universe. Though stable, traversable wormholes remain hypothetical, the mathematics behind them is consistent, suggesting that the cosmos could, in principle, fold upon itself like a higher dimensional origami. The tear in space-time, then, is not destruction, but transformation. It marks the threshold where our understanding gives way to something deeper, where physics as we know it dissolves into forms we have yet to write down. Every singularity, every warped horizon is a reminder that reality's fabric is alive, capable of stretching, bending, and reconnecting in ways that challenge the limits of human thought. Through these cosmic ruptures, the universe reveals its hidden architecture, a stage upon which gravity and light perform their most intricate dance, curving, reflecting, and twisting through space like mirrors turned toward infinity. Black holes and mirrors. A black hole is more than a celestial object. It is a mirror held up to the laws of physics, reflecting both their beauty and their failure. At first glance, these entities appear simple. Regions of space where gravity is so strong that nothing, not even light, can escape. Yet their existence reveals profound contradictions between relativity, quantum mechanics, and thermodynamics. In studying them, we see not only into the heart of collapsed stars, but into the boundaries of knowledge itself. The concept began with Karl Schwarzschild, who in 1916 found the first exact solution to Einstein's field equations. His calculations described how space-time curves around a single massive point. The result was startling. A radius now known as the Schwarzschild radius, beyond which escape becomes impossible. Anything crossing that boundary is lost to the outside universe, though its gravity continues to influence what remains. For decades, physicists regarded this as a mathematical curiosity, until evidence for real black holes emerged through observations of X-ray binaries in the 1,960 seconds, and later, supermassive giants anchoring galaxies. Despite their reputation as devourers, black holes are remarkably structured. Their properties can be described by just three quantities: mass, charge, and spin. This simplicity gave rise to the no-hair theorem, suggesting that all other information about the matter that forms a black hole is lost. Yet that apparent loss created one of physics' deepest paradoxes. According to quantum mechanics, information can never be destroyed. According to general relativity, black holes erase it completely. Stephen Hawking's work in the 1,970 seconds added another layer to the puzzle. By combining quantum field theory with curved spacetime, he discovered that black holes are not entirely black. Virtual particle pairs that constantly pop in and out of existence near the event horizon can be separated by gravity. One particle falls in, the other escapes as radiation. This process, known as Hawking radiation, causes black holes to lose mass and eventually evaporate. It was a revelation. Black holes could radiate heat, obeying the same thermodynamic laws that govern everything else. But if a black hole can evaporate, what happens to the information it contains? If it truly vanishes, quantum mechanics would be violated. If it somehow escapes, relativity's event horizon would not be absolute. This information paradox remains unresolved, though newer theories, such as the holographic principle proposed by Gerard Hooft and Leonard Susskind, offer a tantalizing possibility. They suggest that all information falling into a black hole might be stored on its two-dimensional surface, much like a hologram encoding a three-dimensional image. In this sense, the black hole becomes a mirror not of light, but of information itself. In 2019, the Event Horizon Telescope produced the first direct image of a black hole's shadow in galaxy M87. The bright ring surrounding the darkness is light bent by extreme gravity, orbiting the event horizon before falling inward. That luminous halo is not merely beautiful, it is physics in motion, space curling back upon itself. Black holes, then, are mirrors of the universe's contradictions. They preserve the grand order of relativity while exposing the limits of quantum understanding. They radiate energy even as they consume it, contain simplicity, yet hint at infinite complexity. To study them is to confront the dual nature of the cosmos order emerging from collapse, creation born from destruction, and as their shadows ripple across space-time, the distortions they leave behind guide us toward an even deeper mystery. The strange patterns of energy and symmetry that form the invisible architecture of the universe itself, the quantum mirage. In the smallest theatres of reality, the universe performs a strange illusion. The quantum mirage is what happens when matter, energy, and information appear to exist in more than one place at once, projected through the laws of quantum mechanics like reflections on invisible glass. It is not an optical trick but a genuine effect, a phenomenon where the microscopic obeys rules that seem to contradict every law of common sense. The term itself originated from a remarkable experiment conducted at IBM's Almaden Research Center in 2000. Scientists placed cobalt atoms on a copper surface, arranging them into an elliptical pattern just billionths of a meter across. When a single atom was positioned at one focus of the ellipse, its electronic signature appeared simultaneously at the opposite focus, though no atom was there. Quantum interference had created a ghostly duplicate of its presence. The atom's information, encoded in the wave function of electrons, had spread and reconstructed itself elsewhere. It was, quite literally, a mirage made of quantum probability. At its heart, this effect arises from the wave-particle duality of matter. Every particle, whether an electron, proton, or photon, behaves not merely as a discrete point, but as a wave that can interfere with itself. When these waves overlap, they can amplify or cancel, forming patterns of probability rather than certainty. In the quantum mirage, this interference redirects energy into regions where no physical particle exists, allowing information to appear where it should not. The laws of motion, once thought universal, bend to the strange grammar of the microscopic. Quantum tunneling, another closely related phenomenon, reveals a similar defiance of classical boundaries. Particles confined by barriers can, through the probabilistic nature of their waveforms, appear on the other side without ever passing through in the conventional sense. It is this principle that allows the sun to shine. Nuclear fusion within its core depends on tunneling, enabling protons to overcome their mutual repulsion. Without this daily miracle of physics, no star, no planet, no life could exist. Quantum mirages are not confined to laboratory curiosities. They echo through the cosmos in phenomena such as vacuum fluctuations and the Casimir effect, where empty space itself behaves as an active participant. Even the fabric of space-time at the Planck scale, where quantum mechanics and gravity intertwine, may be riddled with similar illusions, rippling with transient energies that blink in and out of existence. In these scales, the universe appears less like a solid stage and more like a shimmering field of possibilities, constantly rearranging its own geometry. The deeper implication of the quantum mirage is philosophical as much as physical. It forces us to question the meaning of presence. If a particle's properties can exist without its physical form, if information itself can stand in for matter, then the distinction between reality and representation begins to dissolve. This same principle underlies quantum computing, where qubits can hold multiple states simultaneously, performing calculations that would take classical machines millions of years. What began as a microscopic illusion has become the foundation of a new technological frontier. In quantum mechanics, the universe reveals that what we perceive as stable and definite is merely the average of countless uncertainties. Every particle is a vibration of potential, every atom a pattern of probability. The mirage does not deceive us, it simply shows that our understanding of solidity was never complete. And as we step back from this flickering world of probabilities, we encounter a far grander mystery, the vast quiet of the cosmos itself, where light, matter, and time drift across gulfs so empty that even silence seems to take on a physical form. The silence between stars. In the dark intervals of the universe, between galaxies and suns, lies an expanse so still it borders on nothingness. This is the interstellar medium, the vast rarefied space that fills the gaps between the stars. It may appear empty, yet even in its silence it hums faintly with matter and energy, thin traces of hydrogen, drifting dust, cosmic rays, and the faint afterglow of the Big Bang itself. The silence between stars is not absence, it is the quiet architecture that holds the cosmos together. Despite its name, interstellar space is far from absolute void. On average, there is about 1 atom per cubic centimetre, a density trillions of times lower than Earth's atmosphere, yet enough to shape the behaviour of entire galaxies. These scattered particles, energized by radiation from stars and supernovae, form clouds that can stretch across hundreds of light years. Within them, the delicate process of star formation begins. Gravity gathers dust and gas into dense knots, pressure rises, and at some critical threshold, hydrogen ignites into fusion. From this near-perfect emptiness, stars are born. Even in its stillness, the interstellar medium carries the fingerprints of ancient events. The elements scattered through it, carbon, oxygen, iron, were forged in stellar furnaces and expelled by dying stars. Every atom in your body once passed through that same cosmic dust, drifting for eons before finding its way into living matter. Silence, in this context, is not lifelessness, it is gestation on a cosmic scale. Beyond our galaxy, the intergalactic void grows even more austere. Temperatures hover just above absolute zero, and distances between galaxies stretch into millions of light years. Yet even here, faint whispers persist. The cosmic microwave background, a relic from the universe's birth nearly 13.8 billion years ago. Discovered in 1965 by Arno Penzias and Robert Wilson, this background radiation permeates all of space, a constant murmur from the moment the first atoms formed. It is the oldest sound in the universe, though we cannot hear it. Its frequency is imprinted across the cosmos, an echo of creation. Modern telescopes, such as the Chandra X-ray Observatory and the James Webb Space Telescope, have revealed that even the blackest voids are threaded by filaments of dark matter and gas. These filaments connect galaxies in vast networks known as the cosmic web, forming a kind of hidden skeleton for the universe. Through them, gravity flows like a current, guiding the formation of galaxies and clusters. The spaces between the stars, far from being dead, are alive with the faint pulse of cosmic evolution. For astronomers, silence is data. The gaps between signals, the absence of light, the faintest background noise, all reveal what cannot be seen directly. It is in the quiet not the noise, that the universe speaks most clearly. And so the silence between stars is not emptiness at all, but the deep breath of the cosmos between acts of creation. It is the pause in the symphony, the dark canvas upon which every galaxy is painted. As this stillness stretches outward, it leads us naturally toward another frontier, where that same cosmic quiet gives way to structures so vast that even gravity struggles to hold them together, revealing the universe's architecture on its grandest scale. The map that lies, every map of the universe, no matter how precise, contains deception. It is not the fault of the cartographer, but of reality itself. For the cosmos is not static. It shifts, stretches, and bends even as we attempt to chart it. The map that lies is the one drawn by light, the tool by which we see everything, yet which arrives distorted by the fabric of space-time. When we gaze deep into the cosmos, we are not looking outward through space, but backward through time, peering at galaxies as they once were, not as they are. Astronomers build their maps using light that has travelled billions of years across the expanding universe. Yet as that light moves, it is stretched by the expansion of space, a process known as redshift. The farther away a galaxy lies, the more its light is stretched toward longer wavelengths. This makes it appear redder and farther than it truly is. What we call the observable universe is, in truth, a kind of illusion, a sphere defined not by what exists now, but by what light has managed to reach us since the beginning of time. Beyond that boundary, the map fades into speculation. Even within the observable cosmos, distortions abound. Gravity, as predicted by general relativity, bends light around massive objects in a process known as gravitational lensing. A distant galaxy may appear smeared, duplicated, or ring-shaped not because of a fault in the telescope, but because space-time itself is curved by intervening matter. Einstein's equations predict these distortions perfectly, and modern observatories like Hubble and James Webb have turned them into tools. By studying how the light bends, astronomers can infer the presence of dark matter, the invisible scaffolding that makes up most of the universe's mass. The very lies in the map become the clues to the truth. Yet there are deeper deceits still. The cosmic microwave background, the faint radiation left over from the Big Bang, is one of our most precise maps of the early universe. But even it is not a direct image. The patterns we see are filtered through billions of years of cosmic evolution, altered by matter, gravity, and time. What began as a near perfectly uniform glow has been subtly reshaped into the intricate structure we observe today. To read this map is to decode the history of everything that has ever existed, yet never to see it exactly as it was. The problem is compounded by the universe's own expansion. Space does not merely carry galaxies away from us, it stretches the very fabric on which our measurements are made. This leads to a subtle paradox. The farther we look, the less accurate our picture becomes, even though we see more of it. The light from distant quasars and galaxies has crossed billions of light years through shifting terrain, making cosmic cartography an act of reconstruction rather than observation. The maps that lie, then, are not failures, they are mirrors of the universe's complexity. Every image of a galaxy is a conversation between gravity, light, and time. Even the night sky above us is a frozen record of events that no longer exist in that form. Polaris shines from 430 light-years away. Betelgeuse, perhaps, has already exploded, its death not yet visible. The sky itself is a palimpsest of vanished realities. The universe is the only map that cannot be true because it changes faster than we can chart it. What we see is not the cosmos as it is, but as it was, and perhaps as it wishes to be remembered. These illusions of light and time unfold. They lead us deeper into a stranger world, where even the smallest pieces of matter begin to disobey memory, and particles themselves forget who they are. The particle that forgot. In the realm of the very small, identity is not as stable as it seems. The particle that forgot is not a poetic phrase, but a description of quantum reality, where particles can lose their individuality, blending and transforming in ways that defy classical understanding. To forget, in this context, means to shed certainty, to become a probability, a field, or even a wave spread across space. In quantum mechanics, particles such as electrons, photons, and neutrinos are defined not by fixed positions, but by wave functions, mathematical descriptions of all the places they might be. When unobserved, they exist as superpositions of states, occupying many possibilities at once. Only when measured does a particle choose a definite state. In a sense, observation forces it to remember what it is. Until that moment, it has forgotten. This behavior is not philosophical abstraction, it is demonstrable fact. The double-slit experiment, first performed by Thomas Young in 1801 and later refined for single particles, revealed that even individual electrons can interfere with themselves, producing patterns of waves rather than points. When detectors are added to determine which slit the electron passes through, the pattern disappears. The act of measurement erases the superposition. The particle, compelled to decide, stops behaving like a wave. Some particles, however, carry their forgetfulness even further. Neutrinos, among the most elusive entities in the universe, can oscillate between different types electron, muon, and tau as they travel. This transformation, first confirmed experimentally in 1998, means that neutrinos do not possess a fixed identity. They exist as mixtures of states, continually changing form. A neutrino born in the heart of the Sun may not be the same type by the time it reaches Earth. Its very nature is fluid, a constant act of self-redefinition. Quantum entanglement deepens the strangeness. When two particles interact and become entangled, their properties become linked regardless of distance. Measuring one instantaneously determines the state of the other. To speak of either particle separately is meaningless, they have forgotten their individuality. Einstein once called this spooky action at a distance. Yet it has been repeatedly verified. In 2022, researchers demonstrated entanglement across distances of over 1,000 kilometers using orbiting satellites, confirming that information itself behaves as a shared, non-local phenomenon. This erasure of distinction extends to the foundations of matter itself. In Bose-Einstein condensates, atoms cooled near absolute zero merge into a single quantum state, behaving as one collective entity. The boundary between many and one dissolves. At the opposite extreme, inside neutron stars, atomic nuclei are crushed until electrons and protons combine into neutrons, forming matter that no longer remembers its earlier structure. Across scales, from the tiniest particles to the densest cosmic objects, the universe repeats the same pattern, identity giving way to unity. The particle that forgot reminds us that certainty is an illusion of scale. What we call a thing is often just a momentary arrangement of probabilities, stabilized by observation and context. The universe itself may operate in the same way a superposition of possible realities, collapsing into form only where consciousness and measurement intersect. And as these quantum amnesias ripple through matter, they hint at a deeper truth yet unseen, where memory, energy, and existence may all emerge from the same invisible field that underlies the structure of reality itself. When energy disappears, energy, the eternal currency of the universe, was once thought indestructible. Every process, from a burning star to a falling apple, was assumed to obey a simple rule: energy can neither be created nor destroyed, only transformed. But modern physics has discovered places where this law falters, where energy seems to vanish or appear from nowhere, in ways that challenge the foundation of thermodynamics itself. At the cosmic scale, the problem begins with gravity. Einstein's general theory of relativity tells us that energy and mass curve spacetime. Yet, defining energy in a curved spacetime is far from straightforward. In an expanding universe, as described by the Friedmann equations, light waves stretch along with space, losing energy as their wavelengths grow. This redshifted light appears to bleed energy into the void, but there is nowhere for it to go, no reservoir where the lost energy is stored. The law of conservation, so absolute on Earth, begins to unravel on the scale of the cosmos. This apparent disappearance is not a bookkeeping error, it is a symptom of general relativity's geometry. Energy conservation only holds in systems that remain fixed and unchanging. The universe, however, is neither static nor closed. Its fabric stretches, carrying galaxies apart. As photons travel through this expanding space, their energy decreases in proportion to that stretch. From our perspective, they grow colder, dimmer, weaker. Yet relativity insists there is no global frame in which to measure the total energy of the universe at all. The universe does not lose energy. It simply lacks a place to define what total energy means. Another frontier where energy behaves strangely lies in the realm of quantum mechanics. At the smallest scales, particles and energy do not exist continuously, but fluctuate in and out of existence. According to the Heisenberg uncertainty principle, the shorter the timescale we observe, the greater the uncertainty in energy. This allows virtual particles to spontaneously appear and annihilate within unimaginably brief moments, borrowing energy from nothing and returning it before the universe notices. The vacuum, far from empty, seethes with invisible motion, a storm of fleeting existence. Physicists call this restless background the quantum vacuum energy, and it may hold the key to one of the universe's greatest mysteries, dark energy. When cosmologists measure how quickly the universe expands, they find it accelerating, as though space itself possesses a hidden pressure pushing galaxies apart. The simplest explanation is a residual energy of the vacuum, a cosmological constant first introduced by Einstein in 1917 and later revived by modern observations. Yet calculations of vacuum energy using quantum field theory exceed the observed value by an astonishing factor of 10 to the power of 120, the largest discrepancy between theory and measurement in all of science. Somewhere between the equations, most of the universe's energy appears to vanish. Even in the laboratory, energy can seem to disappear. During beta decay, early experiments found that electrons emitted from atomic nuclei carried less energy than expected, apparently violating conservation. In 1930, Wolfgang Pauli proposed an invisible particle to solve the puzzle. That ghostly entity, the neutrino, was later confirmed experimentally, restoring balance to the books of physics. It was a reminder that when energy goes missing, it may not be lost, only hidden. But the universe is not so easily contained. In black holes, energy, matter, and information collapse into singularities that seem to erase all record of their origin. Hawking's discovery of black hole radiation in the 1970 seconds revealed that these objects slowly evaporate, converting their mass back into energy. Yet the fate of the information encoded in that energy remains uncertain, a paradox at the heart of modern physics. Does the universe keep a perfect ledger, or do some transactions simply vanish from its memory? When energy disappears, it is not destruction but transformation beyond comprehension. It may seep into the geometry of space-time, dissolve into quantum fluctuations, or hide behind horizons we cannot cross. What looks like loss might be a rearrangement in dimensions we cannot yet see. As this strange balance unfolds, another mystery rises from the equations, a hidden constant that threads through the chaos, shaping the structure of the universe while quietly defying explanation. The hidden constant. Among the countless numbers that define the universe, one stands apart not for its complexity, but for its persistence. The hidden constant is the fine structure constant, denoted by the Greek letter alpha, a dimensionless number that governs how light and matter interact. Its value, approximately 1 over 137, appears throughout quantum physics, like a quiet refrain connecting electricity, magnetism, and quantum mechanics into a single melody. Yet no one knows why it has this precise value or what would happen if it were even slightly different. First introduced by Arnold Sommerfeld in 1916, the fine structure constant determines the strength of the electromagnetic force. It sets how electrons orbit atomic nuclei, how atoms absorb and emit light, and how energy levels split in the presence of magnetic fields. Every chemical bond, every photon emitted by a star, every spark of light we see, owes its existence to this single number. Richard Feynman once called it one of the greatest damn mysteries in physics, noting that all good physicists should write it on their walls and worry about it. What makes alpha so enigmatic is that it is dimensionless. It does not depend on any particular units or measurement systems. It is pure, universal proportion. If the constant were even slightly larger, atoms could not hold together. If smaller, fusion within stars might never ignite. The universe's structure depends delicately on its precise value. It is as though nature selected a single number to ensure that light, matter, and energy could coexist in balance. Attempts to derive alpha from deeper principles have so far failed. Quantum electrodynamics, QED, the theory describing light and charged particles, uses the constant as an input rather than predicting it. The Standard Model, elegant though it is, leaves alpha unexplained. Even theories that attempt unification, string theory, supersymmetry, or the multiverse hypothesis struggle to account for why this constant has its particular value. Some suggest it may not be constant at all. Measurements from distant quasars hint, with cautious uncertainty, that alpha might vary slightly across cosmic distances, implying that the laws of physics themselves could change from one region of the universe to another. This possibility unsettles the idea of immutable laws. If fundamental constants drift, even subtly, then physics becomes local, a patchwork of realities stitched together by shifting rules. Yet the evidence remains inconclusive. For now, alpha continues to hold steady across time and space, its mystery intact. The hidden constant is more than a number, it is a fingerprint of reality's design. Through it, the quantum and the cosmic intertwine, linking the microcosm of electrons to the great machinery of stars. It is the quiet rhythm beneath existence, whispering through every atom that the universe is both comprehensible and profoundly strange. Chaos in the vacuum. In the emptiest places of the universe, space itself refuses to stay still. What we call vacuum is not truly empty. It is a seething ocean of energy, bubbling with fleeting particles that blink into and out of existence faster than any measurement can catch them. This restless activity, invisible yet omnipresent, is the foundation of quantum field theory, the most accurate framework ever devised to describe the subatomic world. But within it lies a paradox so profound that it threatens to tear the fabric of physics apart. Quantum mechanics teaches that every point in space is filled with quantum fields, vibrations that can never be entirely at rest. Even when stripped of all particles, those fields continue to oscillate, producing what's known as zero-point energy. This constant jittering gives birth to virtual particles which emerge spontaneously, borrow energy from the vacuum, interact for a brief instant, and then vanish. Though ephemeral, these fluctuations have tangible effects. They produce the Casimir effect, first measured in 1948 by Hendrik Casimir, in which two metal plates placed nanometers apart are drawn together not by magnetism, but by the pressure of the quantum vacuum itself. This invisible chaos is responsible for many of the universe's most essential behaviors. In atomic physics, it shifts the energy levels of electrons, slightly altering the light emitted by hydrogen, an effect precisely measured and confirmed. In astrophysics, it shapes the earliest structure of the cosmos. The tiny fluctuations in the quantum vacuum were amplified by cosmic inflation in the first fractions of a second after the Big Bang, becoming the seeds from which galaxies eventually formed. The stars that now scatter the night sky began as wrinkles in this invisible, chaotic foam. Yet the same vacuum that creates everything also threatens to destroy understanding itself. When physicists calculate its total energy, the result is catastrophically large. So large that if true, the universe would have torn itself apart instantly after its birth. The discrepancy between theoretical prediction and observed reality is staggering, one followed by 120 zeros, the greatest mismatch between theory and measurement in all of science. This vacuum catastrophe sits at the heart of modern cosmology, a wound that neither relativity nor quantum mechanics can heal. General relativity, Einstein's great geometric description of gravity, treats energy as the source of space-time curvature. But if the vacuum truly holds such enormous energy, its gravity should be overwhelming. Space should curl in on itself, crushing galaxies before they form. The fact that it doesn't suggests something fundamental is missing. Perhaps energy in the vacuum cancels itself out through a symmetry we have yet to discover, or perhaps the equations we use to describe the fabric of the universe are only approximations of a deeper reality. Some physicists suspect the answer lies in quantum gravity, a theory that unites the smooth geometry of space-time with the granular chaos of quantum fields. In this view, space-time itself may not be continuous, but composed of discrete units at the Planck scale, each vibrating with its own microscopic uncertainty. The vacuum would then be a vast network of interactions, constantly rearranging and recombining in ways that produce both stability and turbulence. Chaos in the vacuum, then, is not disorder, but creation in motion. It is the pulse of existence, the underlying rhythm from which matter, light, and gravity all emerge. The calmness of empty space hides a furious storm balanced perfectly between nothingness and potential. Beyond this invisible turbulence, the universe cools into stillness once again, a place so empty, so dark, and so silent that even chaos itself begins to fade into the cold heart of the cosmic void. The cold heart of the void. Between the galaxies, in stretches of space that span hundreds of millions of light years, lies a darkness that approaches absolute nothingness. The cold heart of the void is not a poetic exaggeration, but a literal truth. These regions, known as cosmic voids, are vast expanses almost entirely devoid of matter, no stars, no planets, and only a faint mist of hydrogen drifting through the emptiness. Temperatures there hover just above absolute zero, where atomic motion nearly stops, and light itself travels for eons without striking a single atom. Discovered through large-scale surveys of galaxies in the late 20th century, cosmic voids form part of the universe's great architecture. When astronomers map the distribution of galaxies, they find a pattern resembling a cosmic web, immense filaments of matter intertwined with equally immense cavities. The Sloan Digital Sky Survey revealed that these voids can stretch for hundreds of millions of light-years, with densities less than 1/10 that of the cosmic average. They are the silent counterpart to the luminous clusters that define the visible universe. The voids exist because gravity pulls matter together. Over billions of years, regions with slightly higher density attracted more material, forming galaxies and clusters, while less dense regions were emptied. Yet these empty spaces are not entirely inert. Within them, dark energy, the mysterious force driving cosmic acceleration, dominates. The expansion of the universe proceeds fastest in these voids, stretching space itself at a rate greater than within galaxy-rich regions. They are, paradoxically, where the universe grows the most. Despite their stillness, voids hold profound significance for cosmology. Because they are largely free of matter, they provide pristine laboratories for testing general relativity on cosmic scales. Observations of light passing through them reveal how the universe's geometry bends and expands. In 2016, astronomers studying the cold spot in the cosmic microwave background found evidence suggesting that a massive supervoid, hundreds of millions of light-years wide, may be responsible for a slight temperature dip, one of the coldest regions ever detected in the observable universe. Even the faint remnants of light that traverse these voids carry history. The cosmic microwave background, the afterglow of the Big Bang, fills them at a temperature of just 2.7 Kelvin. It is the universe's thermal whisper, the lingering warmth of creation diffused across the infinite dark. In this near-perfect silence, every particle of radiation is stretched, cooled, and dispersed, a faint reminder of an origin now impossibly distant. At such scales, the boundary between presence and absence becomes delicate. Space is not truly empty. Even in the deepest voids, quantum fields persist, flickering weakly in the dark. Gravity still binds the farthest edges, and dark matter threads invisibly through the emptiness like faint scaffolding. The cold heart of the void, then, is not death. It is the slow breathing of the cosmos, the interval between acts in an infinite performance. As the universe continues to expand, these voids grow ever larger, their edges receding faster than light can cross them. One day, countless galaxies will vanish beyond our cosmic horizon, leaving behind only the faintest memory of a once luminous sky. The universe hiccup. Every so often, the universe seems to stutter, not in sound, but in expansion, a vast, silent hiccup that ripples through the fabric of space-time. These cosmic irregularities are not random. They are fossil records of events that shaped everything from the birth of galaxies to the rhythm of time itself. Astronomers call them baryon, acoustic oscillations, faint imprints left over from the early universe's brief moment of hesitation. To understand this hiccup, one must travel back nearly 13.8 billion years to when the universe was a hot, dense plasma of particles and light. In that early sea of energy, gravity tried to pull matter together, while radiation pushed it apart. The competition between these two forces sent waves of pressure rippling through the young cosmos, just as sound travels through air. For hundreds of thousands of years, the universe vibrated with these primordial sound waves, an invisible symphony moving through space itself. Then, roughly 380,000 years after the Big Bang, The universe cooled enough for protons and electrons to combine into neutral atoms, releasing light for the first time. Those waves froze in place at that moment, their crests and troughs preserved in the large-scale structure of the cosmos. What remains today are slight patterns in the distribution of galaxies, faint echoes of that ancient oscillation. When we look at maps of the universe on its grandest scales, galaxies are not scattered at random. They cluster in a subtle, repeating pattern, each separation roughly 500 million light-years apart. That distance marks the fossilized wavelength of the universe's earliest sound. These oscillations are more than relics, they serve as cosmic yardsticks. By measuring how their scale changes with distance, scientists can track how the universe's expansion has accelerated under the influence of dark energy. In 2005, data from the Sloan Digital Sky Survey provided the first clear detection of baryon acoustic oscillations, confirming predictions made decades earlier. Since then, surveys like BOSS and DESI have refined our understanding of cosmic acceleration, showing that even the universe's hiccups carry messages about its ultimate fate. But the universe's rhythm extends beyond sound. Another kind of hiccup occurs in the mysterious inflationary period that followed the Big Bang. Inflation, a burst of exponential expansion lasting less than a fraction of a second, smoothed and stretched space-time to cosmic proportions. Yet within that expansion, tiny fluctuations, perhaps quantum in origin, were magnified into the seeds of all structure. Some inflationary models suggest these fluctuations might have produced jitter in the expansion rate itself, momentary hiccups in how quickly the universe grew. The faint temperature variations seen in the cosmic microwave background, mapped in exquisite detail by Kobe, WMAP, and Planck, are the frozen signatures of those tremors. Even in the modern era, the cosmos does not expand perfectly smoothly. Astronomers have detected Hubble tension, a disagreement between measurements of the universe's current expansion rate using nearby galaxies and predictions based on the early universe. This tension, tiny though it seems, may hint at new physics. Perhaps dark energy changes over time, or unseen particles subtly alter cosmic dynamics. It is as if the universe itself momentarily caught its breath, altering its pace in the cosmic horizon. At the furthest limits of our perception lies a veil of darkness, the cosmic horizon, beyond which no signal, no light, and no information can ever reach us. It marks not the edge of space, but the boundary of what can be known. Beyond it, the universe continues, unseen and unreachable, expanding faster than any message could ever return. The cosmic horizon exists because of the finite speed of light and the accelerating expansion of the universe. While light travels at 300,000 kilometers per second, space itself can stretch faster than that speed. As galaxies are carried away by the expansion, their light becomes redshifted, its wavelength lengthened until it fades entirely from view. Beyond a certain distance, roughly 46 billion light-years in all directions, galaxies recede faster than light can chase them. They do not move through space at that speed. Space itself expands between us. This defines the observable universe, a sphere centered on Earth, not by choice, but by the limits of causality. Everything we see, every galaxy, nebula, and star, is contained within this bubble of observability. Yet the universe is almost certainly far larger, perhaps infinite. What lies beyond remains a mystery. Some cosmologists suspect that vast regions beyond our horizon could look similar to our own, governed by the same physical laws. Others propose that conditions could differ entirely, with variations in dark energy, matter density, or even fundamental constants. Inflation theory suggests that our observable universe might be one bubble among countless others in a grand cosmic foam, a multiverse, separated by inflating space-time. The light from the most distant regions we can see, the cosmic microwave background, has travelled for 13.8 billion years to reach us. It represents the universe as it was when it first became transparent, long before the first stars or galaxies. Beyond that, the past disappears not because it does not exist, but because its light will never arrive. Each second that passes, the expansion drives more of the universe beyond reach. Someday, even the nearest galaxies outside our local group will slip beyond the horizon, their light redshifted into oblivion. For astronomers, this boundary is not an obstacle, but a revelation. It shows that we live in a universe defined not by edges, but by limits of information. Our horizon is both our prison and our window, an ever-receding edge that reminds us of how small, yet how connected we truly are. Perhaps, beyond that silent frontier, the universe continues in patterns we cannot yet imagine, vast stretches of space-time, obeying rules that might make our physics look as quaint as candlelight in the dark. As this distant horizon fades from sight, it brings us back inward to the fragile light that remains, and to the faint ghosts of radiation still echoing through the emptiness, whispering of everything the universe once was, and everything it will someday forget. The ghosts of light. In the vast blackness between galaxies, light sometimes lingers long after its source has died. These are the ghosts of light photons that have travelled for billions of years across expanding space, stretching and fading as they go. They are not echoes in the ordinary sense. They are survivors, remnants of events so ancient that their origins no longer exist in any recognizable form. Every photon that reaches us from deep space is a fragment of cosmic memory, carrying the story of the universe, written in wavelength and time. When we look through telescopes, we never see the present. We see history suspended in motion. The light from the Andromeda Galaxy left 2.5 million years ago, when early humans had only just begun to use tools. The light from the most distant quasars has been travelling for over 13 billion years, from a time when the first galaxies were still forming. As it moves through expanding space-time, the light stretches, its energy diminishing until it slides into the infrared, then the microwave. This process, known as cosmological redshift, transforms visible light into a whisper. The universe, in its relentless expansion, turns brilliance into silence. Some of these spectral travellers never reach any destination. Their wavelengths lengthen until they blend into the cosmic microwave background, the faint afterglow of the Big Bang discovered in 1965 by Arno Penzias and Robert Wilson. This background radiation is the oldest light we can observe, emitted when the universe was only 380,000 years old. It fills all of space, uniform and cold, at about 7 Kelvin. Yet embedded within it are minute variations, ripples that mark the earliest seeds of structure. The CMB is not merely ancient light, it is the fossil record of the cosmos itself. Light also leaves ghosts in more immediate ways. Around galaxy clusters, gravity bends space-time so intensely that photons curve around them, creating gravitational lenses. These distortions can magnify and duplicate distant galaxies, producing eerie rings and arcs of light. Some of these images show galaxies as they were billions of years ago, preserved like reflections on a warped mirror. Astronomers using the Hubble and James Webb telescopes have found galaxies so far away that their light was bent, delayed, and replayed through multiple paths like a cosmic time loop. What we see may be the same burst of light arriving at different times, centuries apart. The ghosts of light also inhabit empty space itself. In quantum electrodynamics, photons constantly flicker into existence as virtual particles, influencing how charged particles interact. Even in total darkness, the vacuum is alive with invisible electromagnetic fluctuations. When light passes through such regions, it can scatter off this quantum froth, subtly shifting its path or polarization. These effects, though minute, have been measured in laboratory experiments, confirming that even empty space glows faintly with unrealized light. Astronomers studying the intergalactic medium have also found traces of these ghostly photons. Between galaxies, clouds of hydrogen absorb and re-emit light from quasars, producing delicate absorption lines known as the Lyman alpha forest. Each line corresponds to a veil of gas billions of light-years away, and together they form a record of how matter is distributed through cosmic time. In this way, even the faintest remnants of light allow us to reconstruct the invisible architecture of the universe. The universe is, in a sense, haunted by its own illumination. Every star that ever burned, every quasar that ever blazed, has left a lingering signature scattered through space-time. The night sky we see is not a static picture. It is a slow cascade of fading ghosts, still crossing the gulf of eternity. When nothing becomes something, in the depths of the quantum world, emptiness is not truly empty. The vacuum, that most fundamental of voids, seethes with hidden energy, a restless field that gives rise to fleeting particles and fields. When nothing becomes something, it is not through magic or creation ex nihilo, but through the continuous, spontaneous fluctuations of the quantum vacuum. This invisible background hum is what physicists call vacuum energy, and it underpins the very structure of reality. According to quantum field theory, every particle is an excitation of an underlying field. Even when those fields are in their lowest possible energy state, the vacuum, they can never be completely still. The Heisenberg uncertainty principle forbids exact stillness. Energy and time are linked in such a way that the vacuum must always fluctuate. These fluctuations create pairs of particles and antiparticles that appear, interact, and vanish almost instantly, borrowing energy from the void itself. Though short-lived, their effects can be measured. One of the most famous demonstrations of this is the Casimir effect, discovered in 1948. When two metal plates are placed extremely close together in a vacuum, they experience a tiny force pulling them together. The reason lies in the quantum fluctuations of the electromagnetic field. Between the plates, only certain wavelengths can exist, while outside, all wavelengths are allowed. The imbalance creates pressure that pushes the plates inward, proof that even the emptiest space contains energy. This same principle operates on cosmic scales. During the universe's first moments, quantum fluctuations in the vacuum were magnified by cosmic inflation, seeding the density variations that grew into galaxies and stars. The chaotic foam of the quantum realm became the scaffolding for the visible universe. Every atom in our bodies, every star in the night sky, traces its ancestry to those fluctuations in what we once called nothing. Yet this energy of the vacuum remains one of physics's deepest puzzles. When physicists calculate the expected value of vacuum energy using quantum theory, the result is staggeringly large, so large it should have torn space-time apart. Observations, however, show that the cosmological constant, the energy density of empty space, is incredibly small, but not zero. The mismatch between theory and reality spans a factor of 10 to the power of 120, the greatest discrepancy in all of science. Somehow, the universe's vacuum energy nearly cancels itself out, leaving just enough to drive the accelerating expansion we attribute to dark energy. In this strange balance, the universe sustains itself. Empty space is the engine of existence, capable of giving rise to particles, radiation, and gravity. Even black holes, the darkest objects known, draw upon this principle. Near their event horizons, quantum fluctuations create pairs of particles, one falling in, the other escaping, as Hawking radiation. Over unimaginable timescales, this slow leak causes black holes to evaporate, converting space-time curvature into real energy. When nothing becomes something, it reveals that nothing has never truly existed. The void is a medium of infinite potential, a restless sea from which the universe continually emerges and dissolves. The boundaries between existence and non-existence blur. Creation is not an event, but a process, forever unfolding in the fabric of space itself. The dreaming cosmos. Across the unfathomable scale of the universe, patterns emerge that feel almost deliberate, as though the cosmos itself were dreaming, unfolding possibilities within the quiet architecture of its own laws. This dreaming is not imagination, but emergence, the natural tendency of the universe to generate complexity from simplicity again and again. From the earliest quantum fluctuations to the birth of galaxies, stars, planets, and consciousness itself, the cosmos has evolved from chaos into coherence, shaping order out of the improbable. The story begins at the Planck scale, the smallest measure of physical reality, where space-time itself flickers like a restless thought. Within these infinitesimal vibrations, energy fluctuates wildly, giving rise to fleeting particles and quantum fields. Out of this chaos emerged inflation, the universe's first great expansion, when space grew faster than light, ironing out its wrinkles into smoothness. From these beginnings, the universe transitioned from dreamlike quantum potential into the structure of matter and energy that still surrounds us today. In the billions of years since, gravity has played the patient sculptor. It gathered gas into stars, stars into galaxies, and galaxies into the great filaments of the cosmic web, stretching hundreds of millions of light years across. At every scale, these patterns reveal a kind of recursion, structures within structures, balance arising from apparent disorder. Even the galaxies themselves spin in spirals that echo the same mathematics found in seashells, hurricanes, and DNA. The cosmos dreams in geometry, repeating its language across scales from the microscopic to the galactic. The emergence of life represents another layer of that same dream. Within the dust of dying stars lie carbon, nitrogen, and oxygen, the raw ingredients of biology. Through chemistry's subtle choreography, these elements combine to form self-replicating molecules, leading to consciousness capable of observing the universe itself. Physicists like Carl Sagan and Freeman Dyson have noted that life seems not accidental, but a natural extension of cosmic evolution. The universe, having given birth to observers, gains the means to know itself, a recursive loop of awareness written into the physics of existence. The dreaming cosmos is not static, it changes with its own imagination. Stars die and seed new generations. Galaxies collide and merge, forming new systems of light. Even the vast emptiness between them hums with quantum potential, a reminder that nothingness itself is fertile. The universe seems to test every possibility, explore every configuration, as though seeking equilibrium between creation and entropy. Yet this process has limits. In billions of years, the stars will exhaust their fuel, and the universe will fade toward heat death, a vast, silent equilibrium of low energy and infinite calm. Even in that distant future, however, the quantum vacuum may still flicker, producing brief flashes of new beginnings. Physicists speculate that new universes might bud from the remains of old ones, each with different laws, constants, or dimensions, a multiverse born from the continual dreaming of reality. The cosmos dreams in the language of mathematics, but we are its poetry, the temporary awareness through which it contemplates itself. Every atom in our bodies once shone in a star. Every thought we have is a ripple in space-time. The dreaming cosmos does not end with us, it continues through us, through everything that thinks, breathes, and exists. And from this vast continuity of being, we are led to the final question not of how the universe began, but how it ends, when all its forces converge at the ultimate horizon of understanding, reality's end point. At the edge of physics lies a boundary so absolute that even our equations begin to dissolve, a place where the known laws of reality cease to function. This is the end point of reality, not in space or time, but in comprehension itself. It is the singularity, the horizon, the ultimate collapse of meaning into mystery. The most tangible expression of this endpoint is the black hole. Formed when massive stars exhaust their nuclear fuel and implode under their own gravity, black holes compress matter into a point of infinite density. Around this point lies the event horizon, a boundary beyond which nothing, not even light, can escape. At this frontier, space-time curves so violently that cause and effect lose their sequence. Inside, the known universe ends. Einstein's general relativity predicts these singularities with unsettling precision, but quantum mechanics refuses to agree. The two great frameworks of modern physics, one describing the cosmic, the other the subatomic, fail to reconcile here. At the heart of a black hole, density becomes infinite, and the geometry of space-time collapses into uncertainty. This is where physics, as we understand it, stops working. Yet, paradoxically, black holes are not merely destroyers, they are cosmic laboratories. In the 1,970 seconds, Stephen Hawking demonstrated that they emit faint radiation due to quantum effects near their horizons. This Hawking radiation implies that black holes can evaporate over immense timescales, returning their energy to the universe. But it also creates a profound dilemma. If black holes eventually vanish, what happens to the information about everything they consumed? Quantum theory insists information cannot be destroyed, yet relativity offers no mechanism for its preservation. This information paradox marks one of the deepest fissures in modern science. The end point of reality might not be a place, but a process, the gradual breakdown of certainty as we approach extremes of scale and energy. At the Planck length, roughly 10 to the power of -35 meters, space-time itself becomes granular, foamy, and probabilistic. Theories of quantum gravity, such as string theory and loop quantum gravity, attempt to describe this regime, proposing that space-time is woven from fundamental loops or vibrating strings. Yet none have been experimentally confirmed. Our instruments, bound by scale, cannot yet probe the realm where the fabric of reality is woven. Beyond the physical, cosmology also confronts an existential boundary, the cosmic horizon of time. In the far future, as the universe continues its accelerated expansion, galaxies will drift beyond visibility, stars will extinguish, black holes will evaporate, and all matter will decay into radiation. Entropy will reach its maximum, temperature will approach absolute zero. This heat death represents the ultimate flattening of reality, a cosmos without contrast, without motion, without memory. And yet, even here, theoretical physics leaves room for renewal. Quantum tunneling, vacuum fluctuations, or cyclical cosmological models suggest that new universes could arise from the ashes of the old. The end of one reality may be the birth of another, continuing an eternal chain of emergence. If there is a true end point, it may lie not in destruction, but in transformation. Reality, it seems, does not stop. It folds, renews, and redefines itself. Just as a star's death gives rise to the elements that form new worlds, the universe itself may one day collapse into the seed of its successor. As the final starlight fades, the question of endings becomes irrelevant because the cosmos, like thought itself, never truly ends. It only changes form, dreaming still, in the dark, and still it shines. Even in the face of entropy, collapse, and decay, the universe continues to shine. Against a backdrop of infinite darkness, light persists not only in stars and galaxies, but in the very structure of reality itself. Every photon, every glimmer that reaches across space, is proof that creation endures, even as the laws that govern it seem destined for silence. The story of light is the story of resistance, a cosmic defiance written in energy, time, and motion. Light, at its essence, is the movement of electromagnetic energy, a self-sustaining oscillation of electric and magnetic fields that requires no medium to travel. It is both wave and particle, both constant and change. When James Clerk Maxwell unified electricity and magnetism in the 1,860 seconds, he revealed that light was not an ethereal substance, as once thought, but a consequence of the universe's underlying symmetry. His equations predicted that electromagnetic waves would always move at the same speed, 299,792 kilometers per second, regardless of the observer. It was this revelation that later inspired Einstein's special relativity, redefining the relationship between space, time, and energy. What makes light extraordinary is not merely its speed, but its endurance. The photons released from the sun's core take thousands of years to escape its dense plasma, scattering endlessly before finally streaming into space. Once free, they travel largely unimpeded, crossing millions or billions of light years unless absorbed by matter or stretched by the expansion of space-time. Some of the light striking your eyes tonight began its journey before Earth even existed. Others, from the edge of the observable universe, have been travelling since the dawn of time, redshifted into infrared whispers by the stretching of cosmic space. Even as stars exhaust their fuel and galaxies drift apart, light remains. The faintest afterglow of the Big Bang, the cosmic microwave background, is still with us, filling every corner of the universe at a temperature of just 2.7 Kelvin. It is not visible to the eye, yet it is everywhere, a remnant of the moment when the first photons broke free from matter, roughly 380,000 years after creation. Those photons have been travelling ever since, carrying with them the memory of the infant cosmos. In the life cycle of a star, light is both the beginning and the end. Fusion transforms hydrogen into helium, releasing energy as photons that escape into the void. When massive stars die, their cores collapse into neutron stars or black holes, and their outer layers explode in supernovae, forging heavy elements like gold, iron, and uranium. For a brief moment, a dying star can outshine an entire galaxy, one final flare before silence. Yet, even black holes, those ultimate prisons of gravity, are not entirely dark. Through the quantum process discovered by Stephen Hawking, they emit faint radiation, losing mass over time. Even at the universe's edge, even in its most absolute gravity, something still shines. The persistence of light is not only a physical fact, but a measure of the universe's structure. The same photons that illuminate the cosmos also dictate its fate. As dark energy drives space to expand, light stretches and fades, but never disappears entirely. Over trillions of years, wavelengths will lengthen beyond detection, turning visible light into radio, then into whispers too weak to measure. Yet physics predicts that even as stars fade and galaxies recede beyond the cosmic horizon, quantum fluctuations will continue to generate light particles, momentary flashes in an endless night. For humanity, light has always been the most universal metaphor for understanding. From the fire of early civilizations to the glow of stars seen through telescopes, light defines the boundary between the known and the unknown. Every scientific breakthrough, every equation or experiment begins by seeking illumination, both literal and conceptual. When the astronomer Edwin Hubble revealed in 1929 that galaxies are receding from one another, it was light stretched, shifted, and decoded that told us the universe itself was expanding. When the James Webb Space Telescope captures the earliest galaxies, it is once again through light that we see time itself unfold. And yet, in all this vastness, light's endurance reminds us of something deeper. The universe may one day freeze, collapse, or begin anew, but for now, it continues to shine across time, across distance, through extinction and creation alike. Every sunrise, every photon, is a continuation of the same primordial brilliance that first ignited 13.8 billion years ago. Even when the last star burns out and the final atom decays, the faint hum of the quantum vacuum will still shimmer with virtual photons flickering in and out of existence. Light, in some form, will persist. The cosmos may fall quiet, but it will never be entirely dark. And still, it shines.